Three, two, one. All right, here we are. It is not 311; it's 318. Yeah. Hopefully everyone enjoyed spring break. It's winding down here. We're getting ready to come back. All right, and here's what I was going to do on Friday before I experienced the worst illness I think I've ever had in my life. Like, just an absolute, like, the most horrific 2 hours of my life in a bathroom. But everybody's good now. It was just, yeah, good times. Alright, well, let's talk about something that's not disgusting, which is nth order linear constant coefficient differential equations, and specifically homogeneous ones. I forgot one of the other keywords, right? It's equal to 0. Alright, so we've been hanging out with these, and specifically we've been looking at the second order case, the case of two derivatives. Here we are dealing with any number of derivatives. Note the notation. With the prime notation, typically you go up to 3 with the primes, and then after 3 you just do this sort of parentheses thing to indicate multiple derivatives. Again, one of the reasons the prime notation has some failures to it, where the Leibniz notation is a little bit more robust, especially for this, but this is a notation that's used. We'll stick to it. So, all right. So again, if we read this equation and we again ask ourselves what we're doing here in differential equations, I'm trying to find a function y whose derivatives up to the nth one, when scaled and added together, all of that equals 0. So it shouldn't be too shocking, just like the second order case, that the solution should look like e to the mx, where m will be a root of the auxiliary equation, where the function is replaced with m and the derivatives are replaced with powers. And here again, no derivative, no power. And anything raised to the 0th power is 1. All right, cool. So, exactly what we did for second order differential equations carries over to third order, fourth order, fifth order, sixth order, so on and so forth. And earlier in the semester we talked about briefly that there is reason to go beyond the second derivative. Of course, as we discussed, if y is representing the position, then y prime is the velocity, y double prime is the acceleration, y triple prime is of the jerk, and then the fourth derivative, sometimes referred to as jounce, but snap is also used, and of course then the fifth and sixth derivative are crackle and pop. And while those are silly names, those higher order derivatives do show up. If you're going to get into some civil engineering things maybe at some point in your life, cantilever beams, so a beam attached to a wall and then force applied to the beam, that actually ends up being a fourth order differential equation. And if I remember correctly, something in the Hubble telescope required a fifth order differential equation. So there is reason to go beyond second order Ds. There are physical things where these derivatives do show up, and my cat Olive is attacking me while I'm trying to record her. Great. You can't see her, but she has shown up. She knows I'm trying to do something, and now is trying to mess everything up. Alright. I'm also recording at night when everybody's asleep, too, so yeah. Anyway. I'm just getting in the lab now. Alright. Anyway, okay. So there is reason to go after this, and as it's going to see here, basically once you figure out what goes on with the second order, third, fourth, and beyond get solved in pretty much the exact same manner. But there, as always, are in, outs, and what have yous. So any nth degree polynomial will always have n solutions. And that includes the solutions appearing multiple times, right? So, for example, we've seen second order differential equations that have one root, but the root technically shows up multiple times. And if we allow for complex numbers too, this is completely sound. So, a brief history. So the fundamental theorem of algebra is actually a very interesting result because, first of all, the big joke is that it's called the fundamental theorem of algebra, but every proof, every explanation of why this theorem is true, uses calculus one way or the other. It does not just use algebra. It requires some sort of high-powered result. Typically, the intermediate value theorem is what is used. And the old joke was that there is never going to be a proof that doesn't use calculus in some way or the other. Somebody has a proof that they claim is purely algebraic, and I mildly disagree. It's a paper from 2018, and they used something called the hyperreal numbers, which to me are that's a calculus thing. That isn't an algebraic, purely algebraic thing. But anyway, going off the deep end here with that. But yeah, so that's the first thing, that the name's kind of misleading. You need a lot more than algebra to demonstrate this. So the other thing is that this is a pretty relatively recent theorem in mathematics. This was proven in the I want to say early 1800s, late 1700s, early 1800s. When was Gauss alive? I'm forgetting. But anyway, so Gauss proved this. So Gauss is a mathematician, but you've also probably been, if you've taken physics too, Gauss is like your least favorite person of all time. So Gauss proved this, and this was actually his PhD thesis that he wrote when he was 19. So, great. But yeah, and there's actually a little bit of a debate too at the time when Gauss had done it. No one thought he should really get credit for it because what he uses was the intermediate value theorem, like I just said, and he basically copied something that Euler had done and just sort of took care of some cases Euler never got around to. So initially there was some sort of Gauss is a hack fraud kind of thing. But then Gauss went on to prove a whole bunch of other things, so, yeah. Alright, but yeah, so the actual proof of this is pretty recent, and again, because it does require complex numbers, which, while algebra has been around since, like, the 9th century, the complex numbers, which are basically fundamental to mathematics, it took a while to get on solid ground. But anyway, yeah, so... Okay, now, with that said, okay, how do you use this stuff to actually form solutions? So the second order case, we saw repeated roots, and we saw what to do. You multiply by x, all right? And that doesn't change here. It's just now the number of times the root appears is the number of x's you need to multiply by. So if your root appears once, you don't need to multiply by any x's. If it appears twice, you multiply by 1x. If it appears 3 times, you multiply by 2x's. So you do an x and an x squared. And the reasoning for this is very similar to the argument I demonstrated in class, where you do this technique called reduction of order. And if you're into this stuff, you can go pursue it a little deeper, but it's not too hard to verify that this is what you end up getting. And similarly for the complex case, we know that that's going to introduce a sine and cosine times e to the alpha, where the alpha and, oh, hey, I'm missing some x's. Ooh, boy, better fix that. There needs to be some, oh man, that's going to add, my program that I use to make this stuff's going to yell at me, because it's going to be like over full box. Yeah, no, it needs to be x's inside there. Not too bad, alright, yeah, I'm not going to yell that. Alright, anyway, yeah, so a cosine and a sine with the imaginary part attached to them, and an e to the alpha x alpha being the real part. And just like the repeated root case where some x's show up, you need to multiply by the appropriate number of x's. Okay. Alright, so we're going to do some examples to demonstrate kind of what happens here. And of course, if you're looking at these formulas and going, oh dear God, this looks horrible, I agree, and so I'm not going to subject you to anything beyond 4th order polynomials. So that being said, let's dive into it and kind of get a feel for it. Okay, so first let's start off with just a nice third order case where our auxiliary equation factors like this, and so we have a real root of -1 and a pair of conjugate complex roots plus and minus I. Okay, because I've got -1, I pick up an e to the minus x, and since I have plus or minus I pick up cosine and sine. Yay! So it's basically just what we did with second order, only now there are more than two things, so it gets all slapped together. All of that theory we discussed about linear independence and Wronskians, it all scales up to third, fourth, and higher. It just, right, because there's more terms, there's just more shit flying around, so you just gotta keep track of it. Alright, so but the bigger elephant in the room right now, of course, is probably this equation right here. You're probably looking at this and going, alright, yeah, bro, what? How do you do that? Okay, so quadratics, we have a much more, we work with quadratics a lot more often than we do with any other polynomial, which is why the quadratic equation is so, fundamental and should be in your math container that you got in your brain. But there are some cubic tricks that you should know as well. Let's talk about them. All right, so let's briefly talk about finding roots of cubic polynomials. Okay, so this equation is always going to have a real root. And it's pretty easy to convince yourself this is true from calculus, from the intermediate value theorem. Plug in a big enough number here, and this is going to go positive. Plug in a small enough number, this is going to go negative. It's continuous, so if it's positive somewhere and negative somewhere else, and we've got a nice continuous function, it's got to equal 0 somewhere, so it's got a root. And in fact, Euler is the one who figured this out. So earlier when I was talking about who should get the credit for the fundamental theorem of algebra, it really turns out that Euler did the hard part, which was proving that every odd polynomial has a real root. From which the fundamental theorem of algebra follows after you do some bookkeeping sort of things. That's basically what Gauss ended up doing. There was work to be done, but it wasn't as huge of a task as what Euler had done. But anyway, so this will always have a real root, and so here's my promise to you: any one that I give you, the root is going to be plus minus 1 or plus minus 2. Or it might be 0, and note, if it is 0, then there is no d term. So, right, because then you just plug in 0 into the equation works. So yeah, any cubic that I'm going to give you, like on a quiz that's happening on Wednesday or something, I'm not going to do anything. I'm not going to do square root of 3 as a root or anything awful like that. So that means when it comes to a cubic, you should immediately check if one of these works. And hopefully if you look at this and go, ooh, if there was a minus here, that would 0 out. And, oh hey, that also cancels these out, so -1 is a root. Yay, so that's one answer. How do I get the other answers then? Alright, well, because -1 is a root, that means this has this term as a factor. You're able to factor this out. That requires a little bit of deep math to explain, not crazy deep. This is something called the factor theorem, and it's not too hard to prove the factor theorem. It's some messy algebra you gotta work out. But trust me, it's true. It's not that bad. But anyway, that means you could factor this out, and over here, you're going to get a polynomial that has degree 1 less. So in this case, it's a quadratic. And so you just need to figure out what these coefficients need to be. Now, in high school or middle school or whenever, you probably learned something called long division here. And if you remember how to do that, go ahead. But if not, well, just multiply this out and then match the coefficients. And so alpha needs to be 1, beta plus alpha needs to be 1, beta plus gamma needs to equal 1, and gamma has to be 1. Alright, well if gamma is 1, that forces beta equaling 0, and similarly this gives me beta 0. I don't know why gamma equals 0. My smoke. Yeah. What? What's going on with these slides? There's always stuff wrong, man. No matter how many times you look through them, there's always shit that's not right, man. Jeez Louise, Olive. My cat is like staring me down and purring aggressively. Can I do video? I don't think I can do video. I'm recording this with the Windows plus G, like the built-in Windows capture thing. Anyway. Alright, but anyway, yeah, so from this you get that beta is 0, so that's 0, these are 1, so that's the term that factors out. Yay, there you go. Cool. And by the way, long division is just doing this, but it's like circumventing having to multiply it out and go through all of that, which to me that's a more natural sort of thing. But again, if you remember how to do long division and are good at it, you can do it that way. Alright, yay, so there's an example of basically how you get the roots of a cubic polynomial. Okay. Now there's another trick that I may pull on you, and that is a technique called grouping. Okay. So there's actually a lot of techniques that are known to get the real root of a cubic. There is a famous formula, I mentioned it, called Cardano's formula, which is how people discovered complex numbers were a useful idea, and not just some made-up hokum. That formula like takes up half. It's not as nice as the quadratic equation. It's not worth memorizing. But anyway, so there's these other techniques, but this one is one that you may have encountered. It's called grouping, and the idea is there are certain cubics where you can put the odd-ordered terms together and the even-ordered terms together, and everything factors out nicely. So, for example, if I group my odd terms together and I group my even terms together, I see that I can factor out an m, I could factor out a -6, and oh, looky here, I could factor out m squared plus 1 now, and I got my roots, 6 and plus or minus I. Back in fall 19, I was teaching differential equations. The good old days, fall 2019, when I had to go to the emergency room with the worst headache I've ever had in my life, and they found a cyst in my brain. And then they said, "You're fine, go home." And I am literally not joking. Yeah, I have what's called a arachnoid cyst, which apparently is like I was born with it, and it allegedly had nothing to do with the headache that I had. The headache I got was for some other thing. But anyway, they were like, "Yeah, you got a cyst in your brain. Bye. Come back for an MRI in 6 months." But then like the pandemic hit, so I never followed up with that. So who knows what's going on in my brain? Nothing good, as we already know. But anyway, so back in fall 2019, I was teaching differential equations, and so this material was up. We were talking about it, and I mentioned some things that you could do with cubic polynomials to figure out their roots, and I put this problem on a quiz, and oh boy, was I Mr. Unpopular because of that decision. Because note, one of the roots is 6. It's not 1, -1, or 2, or -2, or 0. Right, so what everybody was doing was trying to plug in 1 and trying to get it equal 0, and it wasn't working, so they were convinced something was wrong, rather than trying to do this grouping thing. So, yeah, that wasn't fun. Anyway, alright, so when it comes to this sort of stuff, these are the kinds of things that I am going to potentially throw at you, so be prepared. And again, these aren't that crazy. There might be, some techniques and skills you haven't worked in a while, but that's what the homework is there for. There's quite a few of these there. Give them a go, and of course the review problems, so check it out. Alright, so let's get back to differential equations. So here is a third order one. If you work out the details, it factors out like this. So I've left it to you to do that. So go ahead and do that and verify that this is what you get. So note 1 is a root, and then you can get the work there to get m plus 4m plus 4, which does factor into this. Alright, so note here, we've got 1 as a root, and we have negative 2 as a repeated root, so we multiply by an x. Yay! That's it. Again, nothing crazy with this stuff. It's pretty straightforward. Alright, so let's, excuse me. Alright, let's get nuts. Alright, so let's talk fourth order. So, in this case, this one factors like this, and, so like I said, you can detect that 1 is a root, and then you can get into a cubic by doing that factor theorem and multiply out trick that I did earlier. There's just more terms, so there's just more arithmetic to be done. And then you can factor up the cubic, and here we've got 1 repeated twice, and then we have this, which has complex roots. Specifically, it's got negative 1/2 plus or minus root 3 over 2, which are a famous pair of complex roots. They're called roots of unity. They show up in the unit circle. Again, take Math 365 next spring, and you'll learn all about this good stuff. Alright, but anyway, so this root repeats, so we multiply by x, and we pick up some complex ones. There we go. Alright, so let's talk fourth order, the polynomials briefly. This is an order higher than I would expect for you to do on a quiz or an exam. Maybe a homework, but when it comes to fourth orders, my all-time favorite trick is the following. Here's a fourth order fourth order quadratic. M to the fourth minus 2m squared minus 3 equaling 0. So, when it comes to fourth order polynomials, ones that look like this are easily solvable. I think I mentioned this when we were talking complex numbers. So when I took complex variables when I was an undergrad, which was the spring of 2007 when I did that, not this problem, but a very similar one showed up on our first exam. So like I referenced that professor, the day before the exam, he gave us a review sheet, and nothing on the review sheet showed up on the exam. So one of the problems on the exam was something very similar to this, and I remember I got here and I looked at it, and I was like, what the fuck is this? What the hell is... Professor Dempsey, what are you doing, man? This has nothing to do with anything that we learned in the course so far. Well, it did, because this is complex roots. And at first glance, it might be like, well, I don't know, can you find that? The trick is to just change your perception a little bit. Specifically, what is m to the fourth really? Well, it's m squared squared. Right, base to exponent is product of the exponents. And now you can see, oh wait, treat this as a single entity. This factors now. This is basically a quadratic. It's just that there's this, right, instead of an x, you have an m squared. So that factors out like this. Beautifully, right? Because if you, pretend this is a z or something. You know, z squared minus 2z minus 3. Well, you know how to do that. Negative 3 times positive 1, those add up to negative 2. And then I can compute the roots. That's super easy. Plus or minus root 3 and plus or minus I. So this trick of turning a fourth order polynomial into a quadratic by being a little sneaky, maybe you should not do that. Maybe you should not do that. Alright, so before we wrap things up with one final example of a super high order one where we have like multiple things. I want to talk a little bit about the theory of solving polynomials. So there is a quadratic equation. I've mentioned that there is a cubic equation. There's a version of that called Cardano's formula, which will get you the real root. It doesn't necessarily get you everything, but it does at least get you that. There is a full-out cubic equation that gives you all three roots, but it's a lengthy equation. There is also a quartic equation. There is a formula that gives you all 4 roots of any 4th order polynomial. It is gigantic. It takes up like 2 pages. It's ridiculous. And naturally, then you want to go, all right, well, 5th order equation, 6th order equation, I'm sure there's formulas for this stuff. Quite shockingly, once you hit 5th order and beyond, there is no more formulas. You can prove, and it's not easy, but you can prove that for any 5th order polynomial, there is no formula for the roots that only uses addition, subtraction, multiplication, division, and roots. There is no formula that only uses those 5 things. There is a formula if you include, what the hell's the name of it? There's like a special, oh shit, I'm forgetting what it is. What is it called? There's like a special function that you have to add in, and then you can get a 5th order, then you get the quintic equation. But for 2nd, 3rd, and 4th, it turns out all you need is addition, multiplication, and roots. Addition, subtraction, multiplication, division, and roots. But for 5th and beyond, you need extra stuff in order to actually get the figure out formulas for the roots. This is a branch of math called Galois theory. Galois is spelled Galois because he's a filthy Frenchman. And that's some crazy stuff. Speaking of interesting math figures in history, Galois died in a duel when he was like 18. And was thrown into a mass grave because, that's what life is. One day you're doing mathematics, next thing you know, you're just in an unmarked grave with a bunch of other French people. Yeah, right. Doing good. But anyway, yeah. So, cool stuff. Yeah, so in practice then, what does that really mean? Well, for higher order DEs, especially if they're 5th order and beyond, you have to just start giving approximate solutions. Like, you can't get exact answers. And even if you could, they might be like, like I said, the quartic equation is like pages long. It's like, sure, I can get you an exact answer, but it's like undecipherable. It's not meaningful. So an approximation that is much cleaner and easier to understand, it's got more use to it. So for higher order polynomials, and thus for higher order DEs, you kind of give up on exact answers and are happy with approximate answers that do a good enough job. Anyway, all right. So let's wrap things up here with one last slide. So here is a beefy 6th order DE. There's its polynomial. So note, here we're going to pick up a e to the x. Here we're going to pick up e to the negative x. This has complex roots, and note they repeat, and that's how they appear in the solution. So this specifically has complex roots 1 plus or minus I. So here's our e to the x term, here's our e to the negative x term. Here are the 2 solutions we get from one complex root, and since it's repeated, then we get them again, but then you multiply by x. And that's the story. Alright, so that is how higher order homogeneous differential equations, linear, constant coefficient, are solved and what their solutions look like. Okay. Alright, and like I said, differential equations like this do actually appear in the physical world, so, we need to know how to solve them, so now you do, and that's it. And speaking of the physical world, when I see you in person on Monday, we're going to talk the all-time classic, day number 1, Duke of New York, differential equation, the mass spring system. Alright, so I will see you then. I hope you enjoyed this video.